Okay, let's talk about Newton's equations of motion. Newton's equations of motion are equations, well, for motion. They are equations that are often called the Suvat equations. And they're called the Suvat equations because those are basically the letters that are used in the equations. And before we get started on them, it's definitely worth focusing just a little bit on this letter here, acceleration. And we need to know, we need to understand, we need to appreciate what the word acceleration means. The word acceleration, in a very clear way, without trying to sound too technical, means one of three things. It either means to speed up, to slow down, or to change direction. Now, I know that this feels a little bit weird because people who don't really know very much about physics think that acceleration just means to speed up. We're used to it in a car, it accelerates, we speed up. But to a physicist, if you slow down, if you apply the brakes and you slow down, you are accelerating. It's just that the value of it is negative. And if you change direction, acceleration is also happening. Now, why? Because of the definition of acceleration. The definition of acceleration is the change in velocity over the time taken. Technically, I would say that as the rate of change of velocity, because the word rate means with respect to time, even though we use it quite loosely to mean other things. So when the velocity of an object changes, not the speed, the velocity of an object changes, that's what we call acceleration. Now, velocity is the speed in a certain direction. So there are two ways that the speed can change. It can get bigger or it can get smaller. But because it has a direction, because it's a vector quantity, it can also change direction. Hence, acceleration is to speed up, to slow down, or to change direction. And if you're never quite sure, just ask yourself mentally, without necessarily speaking it out loud, is this object getting faster, getting slower, or changing direction? And of course, you can actually do two of those things. You could speed up and change direction at the same time, or slow down and change direction at the same time. Okay, so let's get back to Newton's equations of motion. And we start with the definition of acceleration. A is delta V delta t. Now I can write that as the change in velocity. Now very often we will say final minus initial. I'm using subscripts there to represent the final value of the velocity and the initial value of the velocity. I don't have to do it that way. I could do it using numbers if you like. I could say it's v2 minus v1 over delta t, of course. But in mechanics, we have two different symbols for the two different velocities, the initial and the final. Now remember that a change in anything, no matter what it is the final value minus the initial value. And we use a v to represent the final velocity, and we use a u to represent the initial. So v minus u over delta t. Now, if you consider a velocity time graph, then this is the slope. Imagine, for example, that we have this as the initial velocity and that as the final velocity over a time t. Then the slope or the gradient of this line will be v minus u, that's that distance there, over t, which is that distance there. And that, v minus u over t, is the acceleration. So it is really important to remember the properties of a velocity time graph. Velocity time graphs, the gradient is the acceleration and the area under them is the distance traveled. And there is a post on the YouTube channel that talks about time graphs, in particular for mechanics, which go into this in more detail. The first thing I'm going to do is basically take this equation, make the delta t a t on the assumption we start at time t equals 0. So a is v minus u all over t. At is v minus u. So I end up with v is equal to u plus at. And this is one of Newton's equations of motion. you note that we're talking about 4 of the letters from SUVAT. There is no S in this particular one, but the others are there. Now, once we have the definition of acceleration so that we can get V is equal to U plus AT, there are 2 different ways of generating the equations of motion. One way is to use graphs and one way is to use mathematics. Ultimately, of course, they are the same thing. Let's do it first of all by looking at graphs. Imagine, for example, that we have an object that is traveling at a certain constant velocity for a certain period of time, and then it speeds up to a new velocity. And in marking this, let's say that is 0, that's t1, and that's t2, that's u, and moving across here, that is v, the final velocity. Now, we've got 2 different parts of the motion here. We've got the first part from 0 to t1, which is constant velocity. And then we've got this second part from t1 to t2, where the velocity is increasing. So let's take them individually. Now, from 0 to t1, the velocity is a constant. Now, I know that the acceleration is the gradient, and the gradient of this is 0. It's got no slope, it's got no incline. And that's right, because it's not accelerating. If we remember, acceleration is the rate of change of velocity. It's how the velocity is changing per second. The velocity in this particular part of the journey is not changing. So the acceleration is 0. Now, in this situation, when the acceleration is 0, taking the gradient doesn't really do very much because it's 0. But I can work out the area, and the area is the distance traveled. So I can write S is equal to the area, and the area, it's just a rectangle, it's the height times the width. U is that height, and T1 is that, which I could just call T for the time taken. Now, this equation is what we might normally write as speed is distance over time, and that's just rearranging it for U. It's S over T1. And this equation is the only equation that we really use for non-accelerated motion. And this is not what we call one of the SUVAT equations, really. So let's look at the accelerated motion, which is this bit here. A does not equal 0. Okay, so the acceleration is the gradient, and the gradient is this distance divided by this distance. So the acceleration is v minus u divided by t2 minus t1. Now, if I just call, for the purposes of this discussion, t2 minus t1 as the time of the acceleration, t, then that gives me t. And I'm back to my definition of acceleration, v minus u over t. Okay, but we're after the distance traveled. That rectangle plus this triangle. S is equal to the rectangle first, that's ut. Remember, I'm using t to represent that time, the time of the acceleration, plus, and then I've got the triangle, half the base times the height. Half v minus u, that's the height, times the base, t. And if you look, I already know from this that v minus u is at. So instead of writing v minus u here, I can replace it with at. So this is ut plus half a t multiplied by t is t squared. That is another one of the equations of motion. I could call it the second equation of motion, but the equations of motion don't have specific numbers. They're just called the equations of motion. Now, I'd like to take that second equation of motion and play with it. So let's take S is ut plus half a t squared. And first of all, let's get rid of a and put back v minus u over t. So we'll take this equation and we'll say s is ut plus half, and instead of a, v minus u over t times by t squared. And one of the t's cancels, so I end up with s is ut plus half v minus u t. And we can get rid of the brackets. So s is ut plus a half vt minus a half ut. All I've done there is taken the half into the brackets along with the t. Now I have a ut there and I have minus a half ut there. In other words, 1 ut minus a half of a ut gives me a half ut. So s is equal to a half ut plus a half vt. And there's a half t there, so I can write s is equal to half u plus v times t. That is considered another one of the equations of motion. But we can do something else with s is ut plus a half at squared. We can basically combine it with v is u plus at. So let's do that on the next page. Now note that I'm leaving gaps in the equation here. S is ut plus a half a t squared. And what I'm going to do is multiply this equation throughout by 2a. 2a, 2a, 2a. So my equation becomes 2as is 2aut plus, and the 2 and the half cancel, and I get a squared t squared. Okay, now let's bring in v is u plus at. And what I'm going to do is square it. So v squared is u plus at squared. V squared is u plus at multiplied by u plus at. So when we have this situation, we multiply, 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 multiply. V squared is u squared plus u at plus another u at plus the final part, which is a squared t squared. So I've got uat plus uat, that's 2 uat. V squared is u squared plus 2 uat plus a squared t squared. Now, as the mathematicians would say, by inspection, 2 uat plus a squared t squared, a squared t squared. This is the same as this. So I can replace the 2 uat plus a squared t squared with 2as, because it's the same thing. V squared is u squared plus 2as. And that is another one of the equations of motion. Now, if we just remind ourselves where this came from, we were looking at this velocity time graph. An object travels with an initial velocity of u, and then it increases to a new final velocity of v. It accelerates, and it accelerates uniformly. That means a constant slope. That's why I drew this as a straight line. The only other thing that we need to do before we summarize what we've done is consider this situation to the opposite, where something slows down. The key is just a simple velocity time graph. So this is a velocity time graph. It's going to start at a value u, fall to a value v over a time t. And if I say that that is time t equals 0, just to keep it simple. And I know that the acceleration is the same equation that I've always had. If I were to actually calculate this, of course, it would be a negative number, because clearly u is a bigger number than v. So the displacement, or the distance travelled, will be vt, which is the rectangle, plus half, and it's the triangle. U minus V, height, times the width. Now, if you just look at the definition of acceleration, I get V minus U is equal to AT. And I do not have V minus U here, I have U minus V. So if I multiply both sides by minus 1, that's U minus V is minus AT. So I have S is VT plus a half. And instead of U minus V, I'm going to put minus AT multiplied by T. So I end up with a fifth equation, which is VT minus half a T squared. And that is another equation of motion. So let's summarize. Newton's equations of motion. V equals U plus AT is essentially the definition of acceleration. We remember it also links beautifully to the VT graph. It's the gradient of a VT graph. By looking at the area under the VT graph, we have S is UT plus a half AT squared. Now, I did say that there was another way of doing this, which was mathematical rather than graphical. And for those that are interested, V is U plus AT. I can integrate that equation. To integrate that equation with respect to time, I do that. The integral of the velocity with respect to time, that's the flash way of saying the area under the graph is the displacement. So that is equal to S. Now I integrate U with respect to T, and that gives me UT plus, and I integrate AT with respect to T, that gives me a half a T squared. So this equation can be found by looking very simply at the area under a VT graph, but it can also be produced by integrating V is U plus AT, the equation that comes from the definition of acceleration. If you don't understand the integration part, if this bit looks a little bit like black magic to you, then don't worry about it. It's not particularly important. Okay, and we also can combine these two equations together to get V squared is U squared plus 2AS. And when I teach Newton's equations of motion, those are basically the three. I don't teach a fourth and a fifth one because basically you don't need them. These are the only three that you need in order to work everything out. I usually get used to saying them in my head by starting with the definition V is U plus AT. I then remember the next one begins in the same way, the V is U, but it's squared. So V squared is U squared. And by that time, when I've said that to myself, I already remember the end. V squared is U squared plus 2AS. It almost becomes like lyrics of a song. And then I remember that the third one begins how the second one ends. It ends with an S, so the third one begins with an S. S is UT plus a half a T squared. So that's the way that I remember them. But just for completeness, since we've gone through them, I will write the other ones that we discussed. I'll put a line under them because, again, these are my main three. And I can also write S is a half U plus V T. If you look at that, that's the average velocity. If it starts at a certain value, let's say it starts at 10 and it goes to 20, and it does it linearly, it's important that it's linear, of course, then the average of that, the average of 10 and 20, you would add those two numbers together to get 30, halve it, 15. And that's what you calculate when you do that. You've worked out the average velocity times time. So it's a little bit of a link to speed is distance over time again. The distance is the average speed times by the time. And then the final one, which is for a negative acceleration, S is equal to VT minus half a T squared. So there you have it. Newton's equations of motion, produced essentially from the definition of acceleration and a velocity time graph, and then basically combining things together. That's all it is. These are the three that should definitely 100% be practiced. These need to come out of your head. You don't need to look them up in a formula book. You need to start with the definition of acceleration and just work on remembering v is u plus at, and then get used to following a sort of mental route to v squared is u squared plus 2as, s is ut plus a half at squared. That will serve you well with any questions on SUVAT. Until next time, take care.